Okay, right, today we're just going to introduce the next topic in the Further Maths first book for Further Maths A-Level, which is going to be matrices. Just going to look at the start of matrices, just describing them, a little bit of addition and subtraction, and also some multiplication. It does advance itself quite a lot from where we're going to be today, but we need to make sure that we get these basics really sorted. And the methods which we're going to use really sorted before we can move on to consider some of those slightly harder things. So let's just have a quick look at matrices for 10 minutes or so. So first things first, we need to get into the habit of describing matrices in this form: n rows multiplied by m columns. Now, I've written a matrix here, just a random one, 472 minus 103, but using this description, we should be happy that this would be what is called a 2 by 3 matrix. We have to understand that we are going to describe matrices always n rows by m columns. Now, a few specific types of matrices which we might want to be aware of. Firstly, square matrix. Now, a square matrix, this is not a square matrix, obviously. This is a rectangular matrix, I suppose you could say, are going to be the ones which have the same number of rows as the same number of columns. So, for example, a 2 by 2 matrix, 3 by 3 matrix, essentially are square matrices. There is such thing as a zero matrix, and a zero matrix is denoted by a 0, but that is going to be any matrix in which all terms are 0. And finally, the identity matrix, which is quite an important one for us, and it's a matrix which takes this format, so alternating ones and zeros. Now, technically, this one here is called I2. Okay, you'll notice that all identity matrices are also square matrices, and this one here is called I3, etc. And I'm sure you can continue this pattern to develop I4, I5, etc. Okay, so those are three specific matrices which we may need to know at some stage. So moving on a little bit, let's talk about how we can complete some calculations with matrices. Firstly, adding and subtracting matrices. Now, there's only one rule to be aware of here, and that is your matrices have to be the same dimensions to adding and subtract. The reason being because in order to add and subtract matrices, all we're going to do is consider the corresponding values, corresponding positions in each matrix. For example, if we consider two 2 by 2 square matrices, to get this top left output, all we're going to do is consider the two top left terms. 2 plus 3 results in 5, minus 1 plus minus 2 minus 3, etc, etc. So adding and subtracting matrices is an absolute doddle. They have to be the same dimensions is the key thing for that. Now, also very straightforward, multiplying matrices by a scalar. Now, we tend to give letters to denote matrices, so I've said that matrix A is going to be 7, 1, 0, minus 2. All we're going to do when we multiply by a scalar, by like a coefficient, is we're going to multiply all elements of the matrix by that coefficient. So, if we want to consider 3A, this new matrix, what we're saying is we're going to consider 3 of this matrix, which is obviously going to become 21, 0, 3, minus 6. So to start off with, gents, two really straightforward operations: adding and subtracting matrices and multiplying by a scalar quantity. We have to be pretty obviously good at that. So let's move on to consider something a little bit more challenging. And this is where we're going to need to spend most of our time over the first few exercises which we do. Matrix multiplied by matrix multiplication. Now, I want to consider two matrices which I've written in our n times m format. The first one, n1 times m1, multiplied by n2 times m2. Whatever the dimensions are, obviously they can be any numbers. Key thing, and this is two things which I'd like us to consider immediately if we see a multiplication question, is this. Firstly, it's only possible if m1 equals n2, i.e. the number of columns in our first matrix is the same as the number of rows in our second matrix. That's the possibility criteria. Once we've considered that, the output dimension of our resultant matrix will actually be the number of rows from the first matrix multiplied by the number of columns from our second matrix. Okay, so I hope this makes sense. Just take a little bit of time to get your head around this. These two have to be the same in order to complete the calculation, and these two will be the dimensions of my output matrix. So let's just consider a few different matrices. This one, 2 by 2 matrix. This one, 2 by 3 matrix. And this one, a 1 by 2 matrix. So to start off with, let's just consider which possible combinations are actually possible. AB is possible because, again, remember, 2 columns and 2 rows. That is possible. Interestingly, BA is not possible because that would be 3 columns, 2 rows. So an important point here is that the order of the letters are really, really important. Okay, so AB is not commutative with BA. Okay, those are different things. And in fact, in this case, AB is possible, BA is not possible. Let's check out for some other ones. CA should be possible because C has 2 columns and A has 2 rows. So that is possible. And CB would be possible because that, again, is 2 columns, 2 rows. BC and AC, again, similar to BA, not possible. So we have to understand the possibility criteria. Let's look at some of these examples using these different matrices which I've written here as our examples. So let's consider the 3 which are possible. AB. Now, just before we start, I think it's really, really important, once we figured out that it is possible, that we also consider what dimensions we're expecting for our output matrix. 2 by 3 in this case, because, just to double check, we're doing 2 by 2 multiplied by 2 by 3. So the 2 and the 2 are the criteria for possibility, and the 2 by 3, as we discussed earlier, will be our output. Now, this is the important bit, and it's going to take a little bit of getting used to. There is a calculator method as well, but actually I would say that we need to be able to do this without a calculator because for me, it's a bit quicker actually doing it by freehand than on our calculator. We'll show you the calculator method in a minute as well. Now, there's a lot of colours here, so please do watch carefully. In order to get this top left-hand term, we're going to use the top row of our first vector of our first matrix, and the left-hand column of my second matrix. Okay, so top left, top and left is a kind of sort of inference which I want us to sort of see here. And all we're going to do is we're going to do 7 multiplied by 7, which is 49, add 2 multiplied by 4. So our output is going to be 57. To get the bottom left-hand value, we're going to do the bottom row multiplied by the left-hand column. So 1 times 7, 7, plus 4 times 4, 16, 23. I haven't colour-coded these next ones, but let's just double-check we're okay. To get the top middle, we're going to do top multiplied by middle. So 7 times 5, 35, plus 2 times 0 is still 35. Bottom middle, 1 times 5, scratch that, and 4 times 0, so 5. Top left, so top and right, 7 times minus 1, plus 2 times 2 is going to be minus 3, isn't it? And bottom right, 1 times minus 1, 4 times 2, 7 in total. So we need to be able to use this method freehand, I would suggest, without a calculator for simplicity. You can see that was quite a quick process for me. Same thing here. Again, CA, just think about our output here. We had a 1 times 2 multiplied by a 2 by 2, so our output will be a 1 by a 2. To get this, well, there's only 2 terms, aren't there? So to get the left-hand term, we're going to do this whole thing, multiply this whole thing. 7 times 7 is 49, plus 5 times 1 is 54. And to get our right-hand term, 7 times by 2, 14, plus 5 times 4, 34. And I'm not going to go through the last example, but I'll let you consider that one at your own discretion. Now, just wanted to show you very quickly, and forgive the camera shaking slightly, how to do this also on a calculator, because it's always nice being able to check your work, and you know, this will be quite useful as well. We want to be, firstly, on our run matrix mode, and to start off with, what I want us to do is just to press matrix/vector. Now, this is going to take us into a list of different matrices. You can make as many as you want. Hopefully, we're never going to need to go all the way down to Z. But we're going to start off just with A, B, and C at the minute, okay, the 3 which I've written. And I've inputted these into my calculator. Now, there is one critical thing which I really need to stress very carefully. Going back to our start of our slide, we said that we're going to describe all matrices as n by n rows, n columns. For some reason, I'm not sure exactly why, the calculator will actually not do that. So if I just show you a new one, it's going to lead me to a new one. If I consider matrix F, it says m by n. We just need to quickly invert that in our mind. Okay, so m rows and n columns, okay, will be what we want. So going back to the ones which I've already inputted, you'll be able to see that I've just literally copied in matrix A, 7, 2, 1, 4. I've literally copied in matrix B, and I've literally copied in matrix C. Okay, so just straight from like the home screen of a run matrix, this button here, matrix vector, I can input the matrices which I want to consider. Now to do the calculations, let's consider calculation AB. I'm going to press option, matrix vector, matrix, and then I'm going to use the alpha A. Okay, so I want matrix A, and I want to times that by matrix, and then alpha again, B. And that should give me the answer which I had earlier on, okay? And you can follow that through for the rest of them as well. Just very quickly to show you that this would also work with the addition subtraction. Obviously they have to be the same size, so that this would also work the same way of getting the things. And also to do the scalar multiplication as well, if I want 3 lots of matrix A, my calculator can do that as well. Okay, so gents, that's a quick run through of matrices. They're going to be really useful in 3D geometry to consider linear transformations, and they're really useful in computer graphics, which is quite an interesting area of industry as well. So hopefully we're going to get stuck in some slightly harder stuff soon, but this is the stuff we need to consolidate for now.